So with fires like very small because you will very constant connected components where it is very high, it's very connected. So when this is explained, if you only have small components in the SLA, so you are removing a lot of edges. So when current developing, you almost 10,000 edges. Almost all of it is basically, yeah. If you want high equal to very highly connected components, then you might end up removing all the edges and individual edges, which is of course connected components.
Okay, sorry I'm a bit late. It's a week for stock deadline, so I was writing this lecture note until the last minute. Okay, so today we will see application of expanded decomposition. Just to recall, okay. So given any graph, right? Let's say it's unweighted, just for simplicity, and we saw that everything generalized to basically various settings. But okay, let's say you have unweighted graph, then we see that we can partition vertex set into part, V1, V2, V3, such that each part is a phi expander, and the number of edges crossing each part, the fraction of edges that crossing the parts are just something like phi fraction times some small factor like log n. So if we just talk about existential result, then this thing gonna be just log m. But we can ask about this for like, can we find such decomposition fast too? And we saw in the previous lecture that we can do it in actually almost linear time when this crossing factor instead of log m, it becomes subpolynomial, some subpolynomial factor. Yeah. So this is the thing that we talked last time. Basically, the algorithm is just to call balanced sparse cut many times. The number of calls is something like m to little 1, and that's why the total running time is nonlinear. And the balanced sparse cut, we can also compute it in basically the time to compute approximate max flow, and that can be done deterministically too, in nonlinear time too. Yeah. So that is how we get fast algorithm. And actually, everything can be made deterministic within this time. So the reason is that, well, we like in the balance cut algorithm, there are two components. One is cut player, and one is matching player. The cut player, we saw like fast randomized algorithm, but I mentioned that is a fast deterministic algorithm too. For the matching player, that is the either phi sparse cut or embedded matching. You can call approximate max flow, and yeah, the X is the fast approximate max flow. But by the end of this course, we will actually show how to do that. Right now, I just said that you can do it. Yeah. Okay, but anyway, if we don't care much about deterministic or not, this is something that we can do for sure. And I mentioned also last time that if you want like this to be polylog, it can be done too, but the running time is something like this. So there is just some dependency on phi. And it's still open if you can get the factor here to be polylog and the running time to be m polylog too. But yeah, this is something that I think I have some idea to do this, but yeah, it's still open. Okay, but that is just expanded decomposition. Today we will see the application. We will see that expanded decomposition can be used to compress graph. Okay. Like imagine that you have a graph, so there can be something like n square edges in the worst case. But can we make the graph to be sparse? Something like n polylog edges, but in some sense still preserve some property about original graph. So this is very useful. Like you can use it in practice for sure. Like just compress things. This is just very natural concept. But this compressing graph is also useful in theory, because once you compress a graph, then you can just run some algorithm on top of that graph. Let's say that, okay, let me just go into the meat of the lecture. So the first tool that we will use is something that I call repeated expanded decomposition. It's going to be something very simple but powerful. So let's see. right, so suppose that you, like, imagine that you have just some graph. Okay, so what will happen if I just said just try to apply expanded decomposition on this graph? Well, you will get something like this. This is just like, let's say that I set phi to be small enough. If it is small enough, let's say 1 over polylog, then the number of edges crossing this part is something like phi times polylog. But phi is small enough, so the total number of edges crossing the part is less than half. We can choose phi to be small enough so that this is true, right? And each part, the blue part here, is gonna be like a good enough expander. Okay, so this is what we get. Now comes the important step. What if I just look at all the intercluster edges, the red thing here, all right, and take all the edges there, look at the graph induced by these red edges. So this is just a graph induced by these m½ edges. So it's just some graph, right? Like if there are like this edge and this edge and maybe this edge, like it looks like this, let's say. Then the graph here is just this graph. Yeah. Okay, it's just really just a graph induced by the intercluster edges. Okay. It's just some new graph. Now, let's just apply expanded decomposition on this new graph. Okay. What you will get is that you will get some expander induced only by red edges, and there will be intercluster edges between the red edges, and that is going to be the half of the red edges, so MO4 now, right? And then you get an idea. You can just keep applying this, right? You get a green graph induced by intercluster edges of the red graph. Do it again.
Can you explain how did you get the red graph again?
Say it again.
Can you explain how you got G2 again?
G2 is a graph induced by intercluster edges. So look at this graph. These edges, call it E prime. E prime and G2 is just a graph that is just a graph such that the edges of G2 is E prime.
Okay, so it has the same vertex as G.
No, only vertex set that induced by the edges of E prime.
Okay,
Yeah. Okay. Okay. All right. Is it any question more about G2 and so on?
So it's like several matches combined together.
This is no matching, right? Like so, it's not a matching because the edge here, it can be like this. Yeah, like you need not to have like disjoint edges between each part. Yeah.
Let's say it's some K-partite graph.
Yeah, it's a K-partite graph. Yeah, right. Yes, that's correct. Okay. All right. So you create a graph of size half and reapply expanded decomposition and do it again and again. You know that you will stop at some point just because the graph size half every time. So they're gonna be at most log n level, not gonna be more than that. Okay. So let's just conclude what do we get from this procedure. You start with some graph, and you will get log n many graph. Each of these graph are edge disjoint. Like this graph, basically partition edges of G, right? Together. Like each edge appear exactly once in one of the GI. And each of the GI, like in each of this level, is literally just a disjoint union of expander. All right. Question?
Is all the 1 by polylog same or
Yeah, we just set phi to be
one constant?
yeah, to be one fixed number. Yeah. Okay. All right. So basically this is what we get. If you start with any graph, you can decompose it into union of expander. And each node appears in at most log n expanders. Because if a node V appears here, it can only appear it might appear in less than log n expander, but at most log n many expander. All right. More question about this?
Could you tell me again how it partitions the edges of G?
So each part is basically G1. What? So G1 is all edges in this expander, right? G2 is just all edges inside the expander on level 2, and G3, and so on. Yeah. So each of the GI is this joint union of this quality expander. All right. Okay. Okay. So basically, this is what we get. Given a new unweighted graph, G, there is a partition of edges into log n mini graph, such that each of the graph contain this joint union of 1 over log expander. So in the slides, I use 1 over polylog because this is the case if we use some fast algorithm, you will need polylog. But if you just talk about existential, you can set phi here to be you can set phi here to be 1 over 2 log m, right? Then each of the time you will get 1/2 here, and that's fine. So, okay. Right. Yeah. So, yeah, as I said here, if you use fast expanded decomposition algorithm instead, you can get this decomposition in m polylog time where each expander is this quality. Or you can do it deterministically too, but with worse quality and time.
So will there be a point of time when no more each and every vertex itself becomes an expander and it just can't be merged to become another expander? before logging.
That can happen.
That can
Like if you start with the graph which is already an expander, well, then you will stop at the first level. There is no second level. Yeah.
So in that case, what will we do with those edges, final edges?
Final edge. What do you mean?
Edges which can't be decomposed into expander.
I mean, if you start with a graph G, which is an expander,
Which is two expanders.
okay, which is two expander.
Yeah. And now we finally get the single edge.
Yeah.
So what do we do? So
Then this single edge, so then G1 is gonna be this, right?
yeah.
And G2 is gonna be this thing.
But that's not an expander.
This is this is an expander just because that trivial reason.
Yeah.
Any graph that have any connected graph that have less than 1 over 5 edges is a phi expander, right? Like if the graph is small enough, it's just expanded by trivial reason. Make sense? Yeah. Yeah. Any connected graph with at most 1 over 5 edges is a phi expander. Right? Just because if you, you can see this, I guess, yeah. Okay. So, so this is what the structure that we can get from any graph again. So it's like a kind of a general structure of graph. Every graph is a union of expanders. And these expanders are not overlapping too much, but in the sense that each node appears in at most log m expander. Okay. So keep this thing in mind, and now we're gonna use it for graph compression or graph sparsification. Okay. So the first concept of graph compression is a spanner. So let's say that we are given a graph G, then an alpha spanner H of G is just a subgraph of G. So it has smaller number of edges for sure. But at the same time, each node for every UNV, for every pair of nodes, the distance is preserved up to alpha factor. So the distance in H is at least the distance in G, but it's not too big compared to the distance in G. Okay. By the way, here the first inequality is kind of trivial. It's followed from the first property. Why is that?
Because if there are less edges, the distance exists.
Yeah, very good. Yeah. When you throw away some edges of a graph, the distance can only increase. And you want to say that you want to throw away as much as possible, but you want to say that even after this throwing, the distance doesn't increase by too much. The stretch is small. Yeah. Okay. So the goal is really to minimize the number of edges in your spanner. We call it the size. And by the way, the best known spanner is the following. I will not talk about this, but I just want to mention that for any k, there exists 2k minus 1 spanner of this size. For example, you can get 3 spanner of size this much. Like even if the graph in the beginning has n square edges, you can get this number of edges. Or if it is 5, then this is going to be 4 over 3, which is something like this. And this is tight, but I will not talk about this. What I would tell you is just how to get quite bad spanner, like not too bad, but like just polylog spanner, and the size is nonlinear. Okay, so it's worse than the best known, but it's quite simple. It's kind of instructive for the next application that we will talk about. So let's look at this proof. Okay, so the first property about spanner that will be handy for us is that they are composable in the following sense. If you have a graph, okay, and let's say you partition edges of a graph into two parts, in any way, you have a graph and just partition it into G1 and G2, partition edges, right? Then, if now you compute, given G1, you compute H1, which is spanner of G1. And then you compute H2, which is the spanner of G2. Like you have two graphs. You have G, and let's say you decompose it into G1 and G2. And you specify each of these. Then the claim is that if you union the H1 and H2, this union is going to be a alpha spanner of original graph. Okay. In other words, a union of sparsifier is a sparsifier of the union. But that's just a mouthful thing to say. Okay, so let's prove it. It's actually quite simple. So first, note that it is enough to show this. If I can say that instead of looking at every pair of nodes, all right? If I can show that for every edge instead, the distance in H is at most alpha. So this actually should be like this of GUV, but this is just an edge, so this is just one, right? So this is why I can just omit this thing. Yeah. If this is at most alpha, then I'm done. Instead of proving this for every pair UV, I just need to prove this for every pair UV, which is an H in G. Okay, so why is that the case? Why is it enough to just prove, like, if H preserve the distance for every pair of H, then it's enough.
Every shortest path is a combination of edges, so everything gets more by only alpha factor. So.
Right. So basically, because if you look at graph G, right, and you take any, let's say, two nodes, S and T, and then take the shortest path here, and then if I already know that for this shortest path consists of a bunch of edges, and if I know that for every edge in G, I might throw away this thing, but I know that there exists some path in H, and this path is of at most alpha length. Then it means that, like, for every edge, I can do this thing. So the purple path here in H, this distance here in H is going to be at most alpha times distance in G. Actually ST for all ST. So it's enough to just prove this for every H. Okay. Okay. So now it's simple. Let's try to prove this statement. Well, there are just two cases. If an H is in G1, then you know that, like if you look at the sparsifier H1, you preserve the distance up to alpha, and the distance in H1 obviously must be at like the upper bound of distance in H, because H is the union of H1 and H2. So distance in H here is at most alpha if E UV here is in G1. The same is for G2, the same reasoning. So no matter what the case is, for every H UV, you get that the distance UV in H is at most alpha. Okay, so now we prove that spanners are composable. Okay, in this sense, they are composable.
Crossing edge.
No, because G1 and G2 are partition of edges in G.
Not a partition of vertices.
Yeah. Yeah, maybe I should stress here. G1, G2, partition edges of G. Okay. Next, spanner. Let's say that we want to compute a spanner inside an expander. You are given a phi expander, G. Claim that it's going to be very easy to get a spanner of this quality in G. And the reason is that if you look at G, it's an expander. Claim is that if you just take H to be just shortest path 3, this is H. Shortest path 3, or BFS if this is unweighted graph. BFS 3 of G. Then the claim is that H is going to be a spanner with this quality. And the reason is super simple. This is because you recall that if a graph is a phi expander, then the diameter of a graph is small, right? Is something like log over phi. And now it means what? It means that if you take any node here, just arbitrary node, source node, maybe call it S. If you take the distance inside H here, it's going to be at most D too. Okay, so what does it mean? It means that if you take any H in G, let's say U here and V here, the distance inside H is going to be at most this thing times this thing, plus this thing. So this is going to be at most 2D. Right? Just walk along the tree. But the tree is just has small depth anyway. So that proved it already. For every edge in G, the distance in H is 2D, and D is this much. So that's why H is a like log over phi expander.
So here the D is depth of the tree or diameter of the tree, or both are same?
D is the diameter of a graph.
So it has is it same as for depth of the tree?
Depth of the tree, yes. Just, yeah. It's at most, yeah. At most D. Yeah. Right. Yeah. And when you look at any nodes here, you might need to walk up and down. So at most 2D.
Because this is breadth first search tree, right? That is why the depth is at most D.
Breadth first.
BFS tree, that is why the depth is at most D.
Yeah. You think about shortest path tree. Or, yeah. Okay. So actually note that here we didn't really exploit that the graph is an expander. We just really need that it has small diameter. Any graph that has small diameter has kind of trivial expander in this way. Okay, so now things seems easy. You have two things that spanner are composable, but spanner on expander are super easy. Now it's kind of very intuitive what we should do. We should just use this repeated expander decomposition, right? Decompose the graph into this bunch of disjoint union of expander. Then for each of the expander here, look at it. Let's call it X. Take each expander X inside some of the GI. Sparsify it using just phi like BFS tree, and you get a polylog spanner of size linear in X, right? And after that, once you have specified every expander, what to do next is just to union all of the specified graph together. And because you know that if you specify each of the thing and union everything together, it's going to be a spanner of the whole thing. So that's why you are done. You really get a spanner.
So do we have bound on number of expander parts does expander decomposition have?
Say it again.
So we have these clusters of expanders, right?
Mm-hmm.
So how many of maximum of those will be there?
We don't know. Like for example, if the graph is just a path, right? The number of parts here can be something like n over phi even. So there can be a lot of parts. But note that each time that we take an expander X, the size of the spanner inside X is just linear in X. Yeah.
Okay.
Yeah. So in particular, if you look at all the specified expander in G in one of the GI, the total size here is going to be ON, right? And it's going to be like a polylog spanner of size ON for GI. And you union all of the specifier for each of the GI, then the total size is going to be n log n now. Okay, and this is, you get a polylog spanner. The running time is going to be nonlinear too, because what you really do is just call expanded decomposition log n time in the beginning. That's nonlinear. And then in each of the expander, you literally just compute shortest path or BFS. So the total time is linear in each expander, but summing everything is going to be linear then. Make sense? Okay. Quick question. So here I assume that G is unweighted. There is like an easy trick actually to handle weighted graph. So suppose that the graph has integral weights between this thing, like 1 to polylog, 1 to polynomial. How can we get a spanner of G when the size is kind of just blow up by log n? So let's look at this trick. Let's call it G here. And I can, let's call G W, which is a subgraph of G, to just be all of the, to contain all of the edges of a graph such that the weight is between W and 2W. So I just collect all edges of size around W into GW. Okay. And then if I, let's say that I compute a spanner of GW. Okay, sorry. Now I think of GW as unweighted graph. Like everything has uniform weight of size W. And now I can just think of it as unweighted graph. Right? So the weight would be off by at most factor of 2 because they are kind of all the same weight anyway. And then I compute the sparsifier of GW and I get HW. Right? And I can do this for every level of W. Let's say now, let's say we have Wi, and let's say Wi is something like 2 to the I, and then we compute for each I compute of GWI. And then union everything together, and that's gonna do it. Does it make sense? Like when and then return like kind of union of for each I. This is HWI, but this you should scale it up by WI and call this thing H.
So the finite size is the number of edges or the sum of the weights of the edges? The n square.
Oh, we really just count the number of edges. Yeah.
Okay.
Right.
The spanner factor also drops by 2, right?
Yeah, the quality, the approximation will drop by 2. But here we can make this like 1.1 or something smaller, then you can make this drop in quality as small as possible.
1 by epsilon.
Yeah. Okay. And what if we want deterministic algorithm? Like what are we gonna get? Like what is the quality that we will get from this approach?
What is random?
So the randomized step is just expanded decomposition here. So this is like when this is polylog, you can do it in, and phi is polylog. Everything is polylog here, but this is randomized. But if you want it deterministic, then you can make this thing sub-exponential or sub-polynomial, but it's deterministic. So you will do everything for the same, like everything will follow by the same thing, but you just set phi to be interlittle 1 here, so that this is going to be interlittle 1 expander, and you just repeat everything. Then you are gonna get like interlittle 1 spanner in this time. Okay. Okay, that is just a simple algorithm. So now let's, one sec. Okay. So look at another one, cut sparsifier. This is just another notion. Given the graph G, we said H is an alpha cut sparsifier. If first H is just alpha cut equivalent to G, here, that is, take graph G and take a graph H. If you take any cut, the cut size are within alpha factor. Okay, alpha factor. And we said that this is cut sparsify if H should have small number of edges. And by small, usually it means that the number of edges in H is proportional to the number of nodes. Okay. So note that here, to make this possible at all, even if G is unweighted, H must be weighted graph, right? Because suppose that G is a complete graph, just like the degree, just look at the degree cut. The degree cut is already n. If H is unweighted, then and has like a small number of edges, then the degree cut will not match already. So you must kind of reweight somehow. Like you must get the weighted graph somehow.
But that isn't that handled by the order, the cut, like defining the order?
Oh yeah. So actually, that's a good point. If we, let's say, if we relax this a bit, like as we define in the, as we define in the lecture, we said that instead of here, we said that there exists alpha 1, alpha 2, such that G alpha 1, alpha 2, where alpha 2 minus alpha 1 is alpha. This is the definition we talk about. So this is just to say that with this definition, it's just, they are equivalent up to scaling. Yeah, actually, very good point. If we really talk about this definition, then it's possible that H is an unweighted graph. Yeah, that's possible. Very good point. Yeah.
Is it possible for every graph
So that is not clear. Yeah.
Is it because we can decrease alpha 1 to how much ever we want? And then,
especially for complete graphs.
yeah.
Yeah. So I'm not sure actually, like, is it true that for every graph there exists an unweighted sparsifier of that graph? That's not clear to me. Is it false or?
It is not clear, right? Because the edge weights can be very different to actually make for the cut value, and there can't be a single alpha 1 value which can decrease all of them to unweighted distance.
I mean, if G is weighted from the beginning, then there is no way that you get unweighted sparsifier. But if G is unweighted, like at least if G is a complete graph, then actually there exists unweighted sparsifier of G. That is just actually an expander.
But that is because of symmetry, right?
Yeah, so it's not clear to me if every graph, for every unweighted graph, there is unweighted sparsifier. So that's I'm not sure it's just false or it's open. Yeah. Okay. So question. Exists cut sparsifier for every unweighted graph. I believe it should be false actually, but I'm not sure. Okay. So cut sparsifier are composable again in the same sense. Given any graph G, if you partition edges into two parts, G1 and G2, sparsify each part and union them together, it's going to be a cut sparsifier of original graph. And you think about this is exercise. Okay.
This is true for spectral sparsifiers,
Yeah.
because it's only sum of edges.
Yeah, but yeah, it's not, yeah, right. Okay. Yeah, it's true, but yeah, not this class, not today. So it's composable, but okay. And now I want to tell you about at least a known way to compute cut sparsifier. It's simple to describe, but it's not clear how to do it fast. And then we will see that this approach is very clear how to do it fast in expander. Okay. So the known approach is this. If you take any graph G and look at each edge UV, let's call lambda of E to be just a mean cut that separates UV from each other. Size of mean cut. Yeah, the size of minimum cut that separate U and V. Okay. That is, you have a graph. Take any edge, E, with this. If there are like many paths like this, then the mean cut that separate this is gonna be big. But yeah, you really just compute kind of max flow from U to V and you get this number. Okay, so this is just some number. And now the algorithm, the known algorithm is this. For every edge in the graph, you add this edge into your graph edge with probability PE. And roughly speaking, PE should be basically 1 over like at least 1 over lambda e. Like ignore this like not so important thing. It's like 1 over lambda e. Okay. Each edge you just add it with probably at least 1 over lambda of that edge. And if you add this edge into the graph edge, then you set the weight of E to be 1 over PE. Like if the probability is half that you add, if you do add it, then you scale up the weight by a factor of 2. Okay. And you return the graph edge. So let's look at this, like why this makes sense. So at least in expectation, the graph edge is G, right? Because for every edge, like for every edge in G, you add it into graph edge with probability P, E, but when you add it, you scale it up by 1 over P, like by 1 over PE again. So the scaling for each edge is just 1, really. So by linearity of expectation, you get that in expectation, the graph edge is G. Make sense? Okay. And now, okay, in expectation, this is not biased, but Fung et al. Proved that actually it is concentrated. So that is H is basically cut equivalent with G within 1 plus 1 minus epsilon factor.
So on expectation, every cut size will also be equal to the other.
Yes, yes, yes. This is kind of what, this is like not very, like I kind of abuse the notation, but that is what I mean exactly. Yeah. Yeah. Look at each cut. This is on the cut sense. Yeah. Every edge in the cut contribute exactly 1 in expectation. Okay. So H is like 1 plus epsilon cut sparsifier, maybe square here. I will not prove this because actually it's gonna take several lectures to prove this thing. But we will just use this fact that like it kind of makes sense that like for each of the edge, you sample it with some probability and scale it up appropriately. And if this probability is high enough, then it should concentrate. But by high enough, this is the most curious part of the algorithm. By high enough, we set this thing threshold to be something like 1 over lambda for each edge. Like intuitively, if the endpoint between U and V, there are like a lot of paths anyway. Even if you don't sample it with high probability, there should be something that cross this cut anyway. So you don't need to sample it a lot. But if let's say the graph is something like this, it's the dumbbell, and this is UV, and the mean cut between U and V is just like 1. So you should really sample this edge. If the mean cut is small, you should sample it. If the mean cut is large, you don't need to sample it that much. That's the intuition. The proof is a bit complicated. Okay. There is another fact that I will omit. I might prove it in the exercise session. That is, this sum is actually at most n. But if it is the case, what do we get? If we really set PE to be this much, something like 1 over lambda, then what is the size, the number of edges in H? It's just really sum over PE, and which is this thing. But sum of 1 over lambda is n. So this is going to be linear. Okay. We will not prove this yet, but like I hope it's fine. Anyway, like this is an algorithm that works. Okay. It's a cut sparsifier of small size, small number of edges. Okay. So this is just in expectation, but what if you want this bound to be with high probability? Again, right, just simple trick, run algorithm log n times and try one of the call will be good with high probability. So it's fine to get expectation here. Okay, so that is just some algorithm, which is known to be to work. Now suppose that we are on expanders. So we want to apply this approach on expander. But in the first scan, this algorithm looks very slow because computing mean cut for every edge, it's just really a lot of time. Like you call maxflow m many times, that's a lot. However, note that the algorithm here really said that just set PE, as long as PE is bigger than this thing, it's fine, right? Like, if you don't care about, if you set PE to be 1 for everything, you will get a cut sparsifier, although maybe not good size. Yeah. So, so what we want actually is a lower bound of PE, of lambda E. Let's say we get this tilde lambda E of each edge. And if we just set, and suppose somehow that this thing, let's say it's within factor of 2 with lambda E, then you can see that everything is fine, right? Because what we can do is that, so let's say that this is within factor of 2, say. Then if we set PE to be this much, it's still going to be bigger than this threshold that we need in the algorithm. But the size of the graph H is now something like sum over 1 over tilde E. But if tilde E is close enough to, if lambda tilde E is close enough to lambda E, then this is going to be this, which is n. The point is just, we just want some approximation of lambda E, and that's fine. Okay. Now, yeah.
We can take the mean cut value as well, right?
The mean cut value can be very different than you mean global mean cut?
Yeah, global.
Yeah, so it can be the case that the graphs look like this is a click, and there is this node. Here the mean cut is just 1, and that's it's going to be 2 crude lower bound for every edge. Okay, so suppose that the graph is a phi expander. And what we want is to get somewhat accurate estimate of lambda e. So this is going to be quite related to your homework. That is, the claim is that if your graph is a phi expander and take any 2 nodes S and T, any pairs of nodes S and T actually, then the mean cut between S and T is basically around like minimum of degree of S and T. Like you can approximate it by just take minimum of degree of S and T. And this is just will be off by at most a phi factor. So I will just sketch it because it's kind of close to your homework. So this part is clear, right? This direction is clear because degree cut is a ST cut. So you have that. But how about this part? Well, you know that if you take the product graph with degree profile the same as G, then because G is an expander, is a phi expander, then they are like a cut equivalent to product graph within phi factor. And once you have that, then well, you know that if you look at the mean cut between S and T in the product graph, the mean cut in product graph is really of size around this thing. For example, like if you take S and T, like you can think of flow maybe like in the product graph you can really send flow from S to every node and from every node to T. Anyway, yeah. So the mean cut in product graph is this much, and because they are G is cut equivalent to K, then you get this. Yeah. The upshot is that in expander, if you want to know mean cut between S and T, just look at the degree of the 2 endpoints. That's it, right? You get some crude estimate of the mean cut. Which means what? Which means that you can set the lower bound of, you can set tilde of lambda tilde E to be this much and set PE according to lambda tilde E. And now, because PE now is greater than this threshold, you get that H will be cut equivalent to G with high probability just by the theorem that we didn't prove. How about the size? The size is going to be like basically the same but off by a phi factor because we might increase the probability than the previous algorithm by a factor of phi. Yeah. So like this thing and this thing are within phi factor, and because you know that this is at most n, then the size of H is going to be the same as before, but with phi factor. But okay, we don't really need this fact. We can actually prove this directly too. Because you see, if you set lambda tilde e to be like this mean degree, like minimum of the degree times phi, then when you sum over all age, you have this much, right? And what is this sum? Instead of summing over all edges, you can look at each node. How many times that you count that each node is charged? It is charged by 1 sec. So think like this, maybe. If you have a graph, and then for every edge, for every edge E, you orient it direct from U to V if degree of U is less than degree of V. Okay. And you just do this for every edge. You will get something like this for every node. Like each node will have some edge going out and some edge coming in. Okay. And well, this sum, like whenever U is less than degree of U is less than V, you charge it to this node. The number of times that degree of U right? Do I understand? 1 sec.
So every edge is charged to the exponent.
Yeah. So yeah, every node is charged basically 1. Like it's charged by the out degree in this graph. The number of times that it is charged is the out degree of this graph. But when you sum over all, like when you sum over this, then you get 1 for each node. Yeah. Right. Yes. Makes sense, right? Okay. So now, how fast can you compute all of this lambda tilde e? It's really just computing, like for every edge e, just compare the degree of the two endpoints. So clearly you can compute all of this in linear time in total. And you just use the algorithm that I mentioned in the beginning. So it means that the total time is going to be linear if the graph is an expander. To get a sparsifier of an expander, you just spend linear time. And the size is going to be this much. Okay. And now, to get the sparsifier of any graph is the same step, right? You have that cut sparsifier are composable, but it's easy to do on expander. So what you need to do? Well, get this repeated expander decomposition again. Sparsify, and then just for each of the expander, sparsify it using this very simple algorithm that just for each edge compare, like use tilde of lambda tilde e for sampling. So for each expander, you will get sparsifier of this size, which is linear in X. Okay, so the size here is basically near linear in X. And in time, which is linear in the number of edges in X. In time. Once you're done, you just union all the sparsifier expander. And because they are composable, you will get the sparsifier of the whole graph. So at the end, you get the sparsifier of this size, right? And the running time is linear. Question about this? Okay, so this is what we have seen. You get like n polylog size cut sparsifier is randomized and in nonlinear time. So actually this is worse than the state of the art, but algorithmically it's very simple. Once you have expanded decomposition, like the expanded decomposition is not so simple, but once you have that, you really just sparsify on each expander, and that's simple. And because of this simplicity, this approach can be extended to the dynamic setting. Like, I'm hoping to talk about how to maintain expanded decomposition in the dynamic setting. And once you can maintain expanded decomposition in the dynamic setting, you can maintain the cut sparsifier on, like, it just reduced to, the problem reduced to maintaining cut sparsifier on dynamic expander. And it's kind of, like, you can see that because everything is so local here, like you really, for each edge, you just compare the degree of endpoint. Like, thing can be done dynamically when the graph change. Anyway, this is for maybe later. Actually, the first work on cut sparsifier gave like a nice bound, better than this one already. It's n times log n over epsilon square. It's randomized and nonlinear time. This is by Benso and Kager. It's very influential work. I add a lecture note here if you want to understand it. But the best known bound, actually, you can shave even log n here. You can get linear number of edges. And this is even deterministic, but very slow. Like that, and the approach is super different. It's based on something called interlacing polynomial technique. Yeah. And it's very algebraic, and I don't actually understand it. But it's nice to see that it's done. And one actually can do it linear size but really linear size in nonlinear time, but randomized. So it's still open that can you do it in nonlinear size, in nonlinear time, but deterministic? That is very interesting question. But when I said it, I didn't understand it. It's not like this is very complicated. It's just I didn't have a chance to look at it. I think it's very interesting if you want to learn about it. Yeah. And this is the reference. Okay. I actually have some more thing to say, but okay, I think I will just talk about what I will tell you next time. So maybe, so you have seen two, like, a ways to compress the graph. Like, it preserves the graph, information of graph. One way is to preserve distance, and one way is to preserve cut size. And you can reduce the number of edges from n squared to nonlinear. But it only preserves things approximately. Okay, you need to lose some factor. Okay, next time I'm gonna talk about what if we want something exact. But I will tell you how to preserve, like how to find a graph such that it will preserve the size of the mean cut exactly. Like every mean cut size will be preserved exactly. But it doesn't preserve all cuts, right? Just cut which is small. So that's one thing. And another thing that I will tell you is that here it's just still like it's just about throwing number of edges, throwing edges away. But what if the graph is already sparse? Can you do something about that? So there is the notion of vertex sparsification too. So basically the setting is like you have a graph, G, but you have just, let's say, a small set of terminals. Let's say 10 terminals. And now you really want to find a graph, new graph, that still contains T inside it. But the graph size is something like, the graph size of size around T. So T is still here. But the graph size is like reduced to something like terminal set. But the information, so here for sure you cannot preserve all information about the original graph, but at least what we want is to preserve information between the terminal set. Let's say the distance between two nodes in T should be preserved, or mean cut between any two nodes in T should be preserved, something like that. Just want to preserve information between some pair of nodes. Yeah. Now you can hope to reduce the number of vertices. So that's what we're gonna talk to next time. Okay, so any question? All right, then see you next time. Yeah.
Describe one earlier note as well that you sent an email. I will send that within 3 or 4 days.